Question 6. Yes. As you might have noticed, these questions go kind of forward in the book, don't they? And I think that's the idea for this year's exam. So they don't mix things very much. Yeah. But yeah, so the last question is about the most advanced bits in the course. And perhaps it's a bit more, I don't know, demanding than the others, but let's see. And it's about what we did, what I was lecturing on, group actions, and then what Killian did, the CELO theorems. That's what this is about. And yes, well, they're doing something, so I don't have to do anything. Okay, well, this is really just definitions. Really, just go straight from the book, you could say. So my advantage is I have the book, and the left action is, so when you want to define it formally, left action of a group G on a set X is a map from the Cartesian product G cross X. Oh, sorry, messed up. I was thinking ahead and I was writing ahead. This is just supposed to be a normal arrow, and this is supposed to be the Mapster arrow. It doesn't really say much so far, but there are two conditions, and the first condition is that the identity of the group doesn't do anything. Well, it doesn't do anything non-trivial, so it just fixes all the points in X. And the second condition is that well, it's the following. So if you take, it's about how the product of two elements in the group acts on the elements of X. And it acts like this. So of course, as always in maths, there's this kind of duality of, you can say, syntax and semantics. So the syntax is how you formally write things, and then semantics is what they actually mean, perhaps. So yeah, you need to know, you need to go both. So you need to, in general, so you need to know how to write these things very precisely, but at the same time, you should be thinking of, okay, so you think of the elements of the group as some kind of transformations of a certain set X. It doesn't matter whether they're finite or infinite, but they're kind of transformations. So we have plenty of examples. Do you remember any matrices acting on the plane or acting in Euclidean space, for example, or the additive group of integers acting on the integer line, which is kind of on itself, but perhaps not quite on itself, etc., etc. So that is, the idea is you have transformations. The transformations can be composed to give you new transformations, and they can also, they have inverses, and not doing anything is one of them, and that's the identity. Identity fixes all the points. So, pass. The pass operation. Okay, that's the idea of an action, and the formal definition is this one. What else does he want? Everything. That's everything for Roman 1. Roman 2 wants the definition of the stabilizer of an element and an orbit of an element. So again, you should know the formal definitions. Stabilizer is all the elements of G that don't move X anywhere. So this is all the elements of G with the property that if you do G on X, you get X back. Yeah. And then part 3, we'll have to prove that it's a subgroup. And the other one was the orbit. So the orbit of an element X is all the other elements in the set that's being acted upon that X can go to. So we've had many examples again, but perhaps you will remind yourselves of. So this is all the Y's in X, say, such that there exists some transformation, some element of the group, which maps this particular X to Y. I hope. If you see something wrong, just stop me. So if you remember, so kind of the many things. One is you look at the X, and you can prove that X can be moved, so the identity leaves it in place, and then by some G it moves somewhere else, and then some other G moves somewhere else, and all these elements here that X can be mapped to, they form the orbit. You probably remember this picture from right here. Before. There's another picture that you can look at if you look at it. If you set X, for example, as the Euclidean plane, and you take 4 rotations around the origin, then the orbit of a point will be the circle centered in 0 in the origin that this point is on, because that's exactly the point where you can rotate a point to. So keep these examples in mind, but what you need to give is this definition rather than the examples. And what was the third thing? Where's that? No, that's point 3. So point 3 wants you to prove that the stabilizer is a subgroup. I think that's a bit fuzzy in the book, if I remember correctly. Well, maybe not. Oh no, maybe not. So, pardon?
But the proof of it was fuzzy in the book.
I don't know. I can't remember. So there was something which needed a lemma that if you something about inverses, but I can't remember what it was. There was something that was kind of tight-lined and missing about something to do with inverses, and I can't really remember what it was. So if you want to prove that the stabilizer is a subgroup, you can pick your favorite criterion of subgroupality. Yeah, I think here you mean, which you never mentioned, that the inverse. E.
The map produced by G is the inverse. Map produced by G inverse is the inverse.
Oh no, that's it. Yeah, no, it's it. No, okay. So yeah, so well, back to clarity. So there are three conditions that we want. The identity is in GX, no matter what X is. For two elements, their product is in GX. They're both in GX. And for anything in GX, its inverse is also in GX. Okay, so let's do that. So first of all, is E in GX? Well, the test of being in GX is this. So EX equals X by definition of an action. So yes, the identity is in GX. The second point we want is, if you have two elements in GX, is their product also in GX. So if G and H are in the stabilizer, is GH also in the stabilizer? So again, directly going from the test, being in the stabilizer, no, what I want to show you, I want this test being in the stabilizer. You want to calculate GH times X. Now, using condition 2 from the definition, you get that this is G times HX. Now, HX is X because H is in the stabilizer by this assumption. Okay. So this is GX. And G is also in the stabilizer, so by this assumption, GX is X. So yes, GH is also in the stabilizer because it satisfies that condition. And then and this one, so if G is in GX, and this one is a bit trickier, is its inverse also in the stabilizer. So we want to show that this is also equal to X. So one way to do this is we know that G is in the stabilizer, so we can replace this X with GX because that's the same. Now using the second condition of the definition, which kind of looks like associativity, but it's not really associativity because the G's and the X are not from the same set. We get this, and G inverse G is the identity, and now using the first condition of what an action is, we get X. So yes, G inverse is also in the stabilizer. Oops. Therefore, GX is a subgroup G. But clearly it is a subset when you look at the definition. It contains elements of G. So. All right. What's part B? Or part B, I don't know what to say. It doesn't give the solution. It only says the description should contain. But it asks for a couple of things. So it should include the definition of the group action from which it arises, definitions of the subgroups Z and C, and a brief justification. So do you remember which action this arises from? It is the count of the orbit, but you've jumped to the justification. Yes. So hold on with that. We'll get there. So, but which group action was it that? It is the orbit of. When you're talking about orbits, you need an action.
One we were talking, one that gave us the Ceylon theorems.
Yeah. So if you don't remember, that doesn't matter. You'll have to remember in a month's time or so. It's the one by conjugation on itself. So G acts on itself by conjugation. So the action is you get G and X, both are from G, even though I'm writing X, but I'm just trying to somehow distinguish the acting element from the one being acted upon. Okay, how do you?
GX, the inverse?
Where do you put the inverse? At the end?
Yeah.
Doesn't make much difference, but we have to stick with one. No. So now, that's first thing, we've stated which action it arises from. Now we should give the definition of Z, G, and C. So Z, G, this is called the center of G. It's from German, it comes from Zentrum.
Let's do that way. Sorry, just go back. If the inverse is on the left one, then it's a right. Yeah.
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 I don't know. I mean, it's kind of... I'm sorry. Yes, you're right. So it should be that. Okay, the center. So these are all the, so in a way,
Stabilizer. Not in Z. G is called the central element. And the non-trivial orbits of this action are called conjugate classes.
okay, so what is this? This is these are all the elements of community with everything. So alternatively, one can write it like this, which will make more sense. In our context, okay, so these are all the elements where no matter what you conjugate them, well, they stay put. That would be the basis of the class equation. And the C sorry. And C of xi that's the centralizer of xi. Just 150. It should be some subgroup of G because you're taking the index of that in G, but and that's a B subgroup. What is it?
I like that. I like just to remember, think that it's just a special name for stabilizer. Just the stabilizer. Stabilizer is the generic term.
So it doesn't move xi in the conjugacy action. G inverse is xi rather. Now we have to produce the justification, so we're coming to well as orbits. How do they play there?
Which draw a big sketch. It's dots and then
Yeah. Okay, so the set X that is being acted upon in any action is partitioned into the orbits. That's one thing we proved, is that the orbits form a partition. So what does that mean? That means that you can't have an element in two different orbits and every element is in some orbit. It's almost obvious because every element has only its orbit and every other, well, all you have to prove is that every other element in that orbit also have the exact same orbit. That is not very hard to do. So using this fact about partition, we can say that in this case, the set that's acted upon is G. So X is the same as G. So G is partitioned into the orbit of the action by conjugation. Like this. Some may be larger, some may be smaller. These are very small. These are the trivial orbits, the orbits that only have one element in them. And then there are some orbits that have more elements. And when I look at the equation, which you can't see, is I put x1 here, x2 there, x3 there, and xk over there. Now these elements that have a one element orbit, what are they? Exactly, they form the center. So this is Z of G. Oops. Mistaken now, and you can say that you can claim what we prove, but you don't have to prove. You don't have to prove it, I don't think. That the size of each non-trivial orbit so the orbit of xi is equal to the index of the center of xi, the centralizer of xi in G. And that, again, we proved in general that the size of each orbit is the index of the stabilizer of that element. So it's not only true for this particular action, but for any action, it's true. And then and the size of G is the size of the center plus add all the sizes of the orbits, non-trivial orbits, master class equation. All right. To our viewers on BBC Three, I'm just waiting for the students to finish note taking. Doesn't exist anymore, does it?
No, it's online.
Online only,
It's just
which is what this is.
the curated content.
Okay, and last part C. About an hour ago, when Killian looked at it, he said, "Oh, that's the tricky part."
6 marks.
Hmm?
6 marks.
Yeah, Lingham, okay. With 19. 19.
And that's that.
Okay, so what do I want? Want to use the Sylow theorems and the concept of internal direct product that every group of order 15 is cyclic. You may assume without proof the result of question 4C. Oh, where's my question 4C?
It's the one that says normal subgroups of trivial intersection from each other.
What does it say exactly?
So intersection of H and K. If H and K are normal subgroups, and their intersection is the density of the trivial subgroup.
And they intersect in the identity only.
Yeah.
Then
Then every little H and little K commute.
like this. Okay, so this is what we want to use, perhaps. This is a tough question. I don't even know myself.
I mean, it doesn't explicitly state it, but you know, I'm kind of expecting to begin by stating the theorems. You know? I mean, I know it says use them, but you know, like if you're asked to use something like that.
Yeah, well, I don't know. I mean, I wouldn't go all the way to stating.
I mean, you're going to have to technically state them anyway. Referring to them.
No. So it goes like this. Suppose G is a group of order 13. Okay. So So 15 is 3 times 5. That should be known to you from the second year.
Okay.
Number theory course. Now the first Ceylon theorem, what does it say? The first Ceylon theorem says that if you have a prime P such that P to the R divides the order of the group and there is a subgroup of order P to the R. Okay, so by the first Ceylon theorem, G has a subgroup, let's say G1 of order 3 and a subgroup G2 of order 5. And that's almost all that this theorem gives you. It also gives you it as a subgroup of order 1, but that you don't need a Ceylon theorem for. Okay, what's the second Ceylon theorem? So the second Ceylon theorem talks about the P subgroups, and the P subgroups are the maximal subgroups of G whose order is a power of P. But they have to be first powers in this case. So second Ceylon theorem implies that all the subgroups of G, yes, of order 3 are conjugate, and also that all the subgroups of G of order 5 are conjugate.
Quite a lot. I was asking to try together.
It might have been worth more than 6 months.
Yeah, you could argue that.
I could argue that, yes. Okay, and the third Ceylon theorem talks about the number of these groups. And it says that the number of P subgroups is congruent to 1 modulo P and is a divisor of the order of the group. So the number N3 of subgroups of order 3 satisfies its congruence to 1 modulo 3, and it divides 15. Right? And for N5, which is the number of subgroups of order 5, it's congruent to 1 modulo 5, and it also divides 15. So what can they be? So because of this, N3 would be 1, 3, 5, or 15. Well, 15 is 2 modulo, 15 is 0 modulo 3, 5 is 2, 3 is 0, so the only option is 1. So there can only be one subgroup of order 3. And among the numbers 1, 3, 5, and 15, only one is congruent to 1 modulo 5. So that can only be 1 subgroup of order 5. So I don't know why we're looking at the second CFU. Well, you don't need it to do anything. Maybe there's only one. Then.
Yeah, but
Okay, so you don't need the second CFU. What you need to know from when we were talking about normal subgroups is that if you have a unique subgroup of a certain order, then it's normal. So we know from lectures. Actually, we probably know it from a tutorial. Well, I wouldn't choose it. I mean, this doesn't give you anything, does it? I mean, you have just one subgroup of order 5, so of course they're all conjugate. Every group is conjugate to.
Or we're using the more basic thing that when you
Using
conjugate
something different.
When you conjugate a subgroup, you get a subgroup.
Yeah.
Maybe different.
Okay, I don't know. Well, yeah. So what we know that there is a unique group of order n, whatever, then it is normal. Thus, G1 and G2, those are the subgroups that have names and are both normal. G. And now I think it's time to use full C, is it?
The question is to show that the group has to be separate.
Oh, maybe you are using second C. Yeah. Maybe. I don't know.
You need to conclude that they're both normal.
They're both normal. I just concluded.
Yeah.
Well, I know that from before.
Right. Yeah, so you're probably not.
One with his own order.
Probably not explicitly. Using the fact that like you conjugate a subgroup, it's a subgroup. Subgroup in the same order.
Oh, no, I don't think you're using second C theorem at all. You can't really. Anyway, you have the conclusion that both G1 and G2 are normal, and now you want to use the thing that the elements commute that are in G1 and G2 because they're only in secondary identity. How can they only in secondary identity? Well, because G1 contains one element of order 1 and two elements of order 3, and G2 contains 1 element of order 1 and 4 elements of order 5. If something is an element of order 3, it can't be an element of order 5 at the same time. So the only thing they can intersect is the element. So it's both G1, G2 are cyclic on different orders. No, I mean, cyclic on different orders. We have that they only intersect in the identity, both normal, hence by question for C, whenever I take G1 in G1 and G2 in G2, I don't know what that was, probably a comma. That last bracket is probably a comma, because it can't be anything else. We get the G1, G2 equals G2, G1, and now I still don't know what to do.
I got the word prime on the board. Different prime.
Yes, that's correct. Thank you. That's a good point.
So in the question was the hint about internal direct product.
Yeah. So now it says that G1 and G2 meet the criteria to form an internal direct product in G, which I don't know what that means. So,
Yeah, it means
so if you take G1, G2 is an internal direct product. In G, meaning that G1, G2 is isomorphic to G1 cross G2, is it not? But because there are already 15 elements, so we have that the internal direct product is a subgroup of G. Isomorphic to the external direct product. And well, it means a bit more, but that's all we need. And the size of this subgroup, the order of this subgroup is already 15, which is the order of the whole of G. That means that G1, G2 necessarily has to be everything. Necessarily G equals G1 and G2. So G equals G1, G2, which is isomorphic to G1 cross G2. Now we've already said that G1 is order 3,
Z3.
which has to be isomorphic to Z3, and G2 is order 5, which has to be isomorphic to Z5. And the direct product of two cyclic groups is cyclic dominant. This is isomorphic to Z15. Surely this is worth more than 6 marks.
It more looks like it's worth that. question. The whole 20 mark question.
Yeah, pretty much, yes.
Tying all these things together.
More like 20 than 6.
Nice question. It kind of ties
It is nice, but
together.
it's more like a coursework question, or at least, you know, a big one in a 6 months. Okay. Just don't tell the dean, which I'll have to cut off the recording. Okay, anything, any comments, observations? This one, I think I'm going to make sure now that it's not